Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fourth of 4 videos in the series on understanding inductance, and the last in the design-related stuff. In the last video, I attempted to explain how to find the total inductance of inductors in series and parallel, RL time constant, how long does it take a current in the inductor to change, inductive reactance, what was the impedance of an inductor, and the phase of current versus voltage in an inductor. In this video, I want to cover a brief touch on transformers. And then what about real inductors made with real stuff? In addition to this video, there's a downloadable document with a whole bunch of formulas for you. The link for that document can be found in the comments portion of this video. Well, let's dive into a brief touch on transformers. Well, no discussion of inductors would be complete without at least a brief touch on the topic of transformers. Well, what exactly is a transformer? Well, in its simplest form, a transformer is composed of 2 inductors that are magnetically coupled to one another, like I show here. One of the 2 inductors is referred to as the primary because this is the one that you apply your AC voltage to. This is the one that you energize with your AC voltage. The other one is referred to as the secondary. This is the output side of the transformer. And as the magnetic field on this side of the transformer varies with the AC, it is sweeping across the conductors of the secondary side of the transformer and inducing a voltage in this secondary side. Remember, it is the magnetic field that is responsible for transferring the energy from the primary side to the secondary side. Now, they may choose to do this just as an air core, again, depending upon the frequency, or they could decide to add some kind of magnetic material in here, as is indicated by lines that they put between the primary and the secondary. The exact composition of this magnetic material will depend upon the frequency that they're designing the transformer around, as well as the amount of power they're trying to transfer through the transformer. Now, what kind of things do they use for describing transformers? Well, to begin with, there's the turns ratio. So sometimes transformers are specified in terms of their turns ratio. The turns ratio is equal to the number of turns in the primary divided by the number of turns in the secondary. It is often indicated by some number, colon, some number. And if the turns ratio is greater than 1, then usually it'll be the turns ratio, colon, 1. If the turns ratio is less than 1, then they will have it 1, colon, and then it'll be 1 divided by the turns ratio. So let's say we had a transformer that had 10 turns on this side and 20 turns on this side. The turns ratio would be the primary turns divided by the secondary turns, which is equal to 1/2 or 0.5. In this case, you would see a specification like this transformer has a 1:2 turns ratio. Now, what about the voltage ratio? If we have a particular turns ratio, how do we know what the voltage ratio between input and output are going to be? Well, it turns out that the voltage ratio and the turns ratio are the same thing. So if we had a transformer with a 1:3 turns ratio and we applied 10 volts AC to the primary side, we would expect to get 30 volts AC on the secondary side. If a transformer was designed to provide, let's say, 9 volts AC on its output, and you had 120 volts AC on its input, then the turns ratio is 120 divided by 9, or 13.33333333. So it would be designated possibly 13.333 on infinitum to 1. Or if we wanted to do a little math so we had nice whole numbers, we could multiply it all by 3 and end up with a 40 to 3. Nicer numbers. But what about the impedance ratio? Sometimes they're specified in terms of the input impedance versus the output impedance. In previous videos, we discovered that the inductance of an inductor is most commonly equal to some number of turns in the inductor squared times some blob of other math that goes along with it. So if we double the number of turns, then we quadruple the inductance of an inductor. In a previous video, we also learned that the impedance of an inductor, or the inductive reactance, is equal to the inductance times this 2 pi times the frequency. Now, if L here is equal to this, and X sub L equals this, then we can take this portion here and stick it in to this equation in place of the L, and we get the impedance is equal to N squared times this blob of stuff times 2 times pi times the frequency. So you can see that the impedance of an inductor is proportional to the square of the number of turns. So if you double the number of turns, then you quadruple the impedance of that inductor. Well, let's just do a quick little example here using the turns ratio and this very knowledge. So if we have a turns ratio, let's say, of 1 to 2, so that means that we might have 10 turns on this side and we have 20 turns on this side. Now, the primary, in this case, we have determined is 120 ohms. So the question that we have is, what is the impedance of the secondary? Well, this is the 1 part, this is the 2 part. We have doubled the number of turns, so 2 squared times the 120 ohms. 2 squared is 4 times 120. That means that this secondary over here has an impedance of 480 ohms. Now, transformers are made of, well, less than perfect materials. And so there are going to be some kind of losses. Nothing is ever 100% efficient. So, what do we do with those? How do we explain that? So not all of the energy that you're pumping into the primary of a transformer is going to be coming out of the secondary. That's why transformers get warm. The power that are being lost in the transfer from the input to the output through the magnetic material is being radiated in heat. All kinds of stuff has been done to try to minimize these losses, but there is a limit as to what can be done. Now in the data sheets you might find a transformer being given an efficiency number in percent, which is equal to 100 times the power out from the transformer divided by the power into the transformer. Now power in is the voltage times the current on the input, and the power on the output is the voltage on the output times the current on the output. So you got power out divided by power in times 100 gives you the efficiency. Now sometimes they'll express this in terms of what's called insertion loss. In other words, the assumption is you're going to lose something. And this is in decibels. Now as a decibel, it would be defined as minus 10 times the logarithm to the base 10. Now that's what you would normally find on your scientific calculator when you see just the word log. We're not talking about cutting firewood here. Log to the base 10 of this same ratio of the power output divided by the power input. And to kind of give you an idea of the relationship between these things, if you go through and do all the math, 1 dB of insertion loss is equivalent to saying that the efficiency of the transformer is about 76%. So now let's take a look at the real inductors made with real stuff. And so now we get to discover real-life inductors. So far we've been talking about perfect inductors, but real-life inductors are made with real-life materials and as such do not entirely behave as a perfect inductor. Now, at the very center of the reality of real inductors is the truth that a piece of wire has a finite amount of resistance. It may not be a lot of resistance, but resistance nonetheless. An inductor is constructed using wire, and sometimes a lot of wire. As such, we have to include in our real-life model some series resistance that is the resistance of the wire itself, of the wire that makes up the inductor. And so we add a resistance in here. And so we have a coil of wire here, and we have essentially a bunch of series resistors in our that make up this coil, right? Now we have a bunch of series resistors. We have current flowing through the wire. That means, because we know that according to Ohm's law, that voltage is equal to the current being sent through the wire times the resistance of the wire. That means that the voltage, the potential at this point in the wire is different than this point in the wire, is different than this point in the wire. In fact, the voltage at this point in the wire is different than the voltage at this point in the wire, which means between two adjacent windings in exactly the same place on the coil, there is a voltage difference. So here we have a potential difference between two conductors. So you have a conductor, you have a potential on it, you have another conductor with a different potential on it, and these two conductors are separated by an insulator. And what does that give us? Well, that gives us a capacitor. So in essence, all through this inductor are interwinding capacitance, attributable specifically because of the fact that wire has resistance. So that means that in our model we have to add a parallel capacitor, the interwinding capacitance of the inductor. So this is kind of like mushing all of these little capacitors that are here together into a single capacitance value is what they do. So you have the ideal inductor, you have the resistance of the wire itself, and then you have the interwinding capacitance. But you know, the impedance of an inductor is frequency dependent, and so is the impedance of a capacitor. So how does that affect what a capacitor looks like as we change frequency? So as we can see from these equations here, the capacitive reactance, as frequency goes up, this gets smaller and smaller because frequency is on the bottom. As inductive reactance, as frequency goes up, this gets larger and larger. So if we were to plot the impedance of this entire circuit here, based on these equations, plus we add in the R, if we were to plot impedance versus frequency, what you would see is the impedance would do one of these. Over here, this is inductive. Over here, this becomes capacitive. Why? Because as we go up, this guy gets smaller and smaller and dominates the equation. When we go down, this one dominates. So as we go up in frequency from a very low value of frequency, initially it looks like an inductor, a lossy inductor with resistance in it. Eventually we get to a point where the inductive reactance and the capacitive reactance become equal. That is this point right here, a point of maximum impedance. You know, antenna traps use this. This is what is referred to as a self-resonant frequency of an inductor. And so some manufacturers of antenna traps will specifically wind an inductor with a specific amount of interwinding capacitance and inductance in such a way as to get the self-resonant frequency at the frequency that they want for their trap. And they do that to avoid having to put a discrete capacitor into the trap. So a parallel capacitor and inductor become a high impedance at this resonant frequency. Now past that point, as you continue to go up in frequency, this is getting smaller and smaller, this is getting bigger and bigger, and so the capacitance begins to dominate. So past this frequency you have an inductor that looks like a capacitor. Below it, an inductor looks like an inductor. And you know, it's interesting that how narrow this is here depends on this resistance of the coil, of the wire in the coil. If you were to take this same thing here and have more resistance, have a lossier inductor, you would actually see this broaden way out like this. And the more resistance you have in your inductor, the lossier the inductor is, the wider this becomes. The lower your resistance in the inductor, the narrower this becomes, and the longer it looks like an inductor. So, the one last aspect of this, of the characteristics of this real-life inductor, has to do with the aspect of the characteristics of the core material. So the characteristics of core materials is more than just the relative permeability of the core material. Core materials can also be frequency dependent. In a perfect world, the core material would have a given permeability regardless of the frequency that you are working with. But in the real world, certain magnetic materials used for inductor cores work a lot better at certain frequencies than they do others. That is why when you select a toroidal core, you first look at the frequency you plan to use to make sure that the toroidal core works at that frequency range. There's also the flux density. This has to do with how much power you can put through the particular core. Some cores work well with very small signals, but they get saturated with flux and no longer are effective once you try to put more power through them. In fact, some of them have actually blown up or melted when people tried to put way too much power through a core. There's a whole lot more. There's a whole science behind inductor core materials, and it's mind-boggling. There's magnetic eddy currents and split cores and all kinds of stuff that goes on. I just depend on the manufacturer's selection tables in light of my specific application. There are more and varied other aspects of real-life inductors, but these are the most important. These are the ones that you're going to see most often. The wire resistance, the interwinding capacitance, the self-resonant frequency, and the core characteristics are those things that you, as an experimenter, are going to most often run up against. Well, there you have the third part of the design-related stuff. Now you know more about transformers. And what about the real inductors? That was kind of an eye-opening thing too, to find out that they turn into capacitors as you go up in frequency. Now don't forget that in addition to this video, there is the downloadable document. It's got all the formulas and stuff in it. The link is in the comments portion of this video. In the meanwhile, thank you so much for watching. Toodaloots.